Great, thank you. And very grateful to the organizers for a wonderful conference and the opportunity to speak today. Yeah, so my topic is dual complexes of semi-log canonical surfaces. This is going to have some overlap with Professor Griffith's talk this morning, namely that my main example is going to show up in these moduli of these I-surfaces, and this was kind of the motivation for thinking about this problem. So I'm going to start off with the dual complex. So the idea is that the dual complex is something we associate to a pair, where you have a variety and then a divisor on it. And, so I'm going to assume my x is some smooth complex projective variety, and that my divisor making it a pair is effective and for now has strict normal crossing. So every component has multiplicity 1, that's another condition I want, and all the intersections are transverse. And once you have these conditions, then you can define the dual complex. So the dual complex of the pair is simply the intersection complex. The idea is that you have some simplicial complex produced from this divisor in your variety. The way you produce it is that for each component, for each irreducible component, you have a vertex, and then the larger simplices record the intersection information. So if divisor 1 and divisor 2 intersect, you connect them with a line. If divisor 2 and divisor 3 intersect, you connect them with a line. If all three intersect, you put a triangle in there, etc. And the only thing that's a little bit tricky is that, well, you might have that. Let's say you're a surface and your divisor is two curves that intersect in multiple points. Then for each point of intersection, you assign a component, a piece of the dual complex. So you would connect, if the two curves intersect 3 times, then you would have the 2 vertices, and then you would draw, 3 segments connecting them. So, the simplest examples are where x is a surface and delta is, some curve. And so here I wanted to do a slightly more complicated example than a toric one for the first example. So the idea is if you take x as P2 and delta is just some number of lines, and I say in general position so that you actually get a strict normal crossing divisor. If they're not in general position, in this case, well, you'll have 3 of them containing the same point or 2 of them overlapping. But then in this case, well, of course, every 2 lines in the plane intersect once, and so for every 2 of these divisors, you're going to connect them up in the dual complex. So in this case, because we're in dimension 2, and everything intersects transversely, we can't have 3 of these lines intersecting. So we're never going to get any higher simplices than just dimension 1, so we're going to have a graph. So in this case, we have, let's see, we have that x is P2, delta is these 4 lines, and so each of the vertices of this graph corresponds to one of the lines, and then each of the 6 segments corresponds to the corresponding intersections. So this example will actually appear later, in my example at the end when we're talking about the generating I-surfaces. Okay, so one more thing that I should mention is that another great source of examples for this and motivation for this is toric varieties. So when you have a toric variety, you have a variety x, and let's say it's a smooth toric variety, and so let's say it's a smooth projective toric variety, so you have a variety x, and it has a boundary delta consisting of just all of the torus invariant divisors. And in this case, you can, you have this combinatorial data attached to that toric variety, which you can recover it from, namely the fan in the vector space NR. And that fan records the intersection information of the torus invariant divisors. So for every ray of the fan, you have a torus invariant divisor, and then a bunch of rays span a cone of the fan if and only if the intersection of those divisors is non-empty, and you get some strata of the boundary of your toric variety. And that's almost the same thing as the dual complex. The difference here is that in the dual complex, we're assigning a point to each divisor instead of a ray. And in this case, well, the difference is just that the way these are related is that the fan of the toric variety is the cone over the dual complex. And of course, it has some extra structure coming from the fact that this ambient vector space NR really comes from the space of valuations on the monomial valuations on the toric variety. This is actually structure we will also have for the dual complex. Okay. Now I want to think about this in a few contexts. So the first context I want to think about this is in birational geometry, because that's mainly my background, is that I'm a birational geometer, and this is how I think about algebraic geometry, is in terms of birational transformations. So one of the places where you can see these dual complexes and where they can be useful is, you think about resolution of singularities. So the idea is, suppose you have some variety and it has a singularity, and, of course, we're in characteristic 0, so then we have this notion of resolution of singularities, and you can produce a log resolution. So, let's suppose we have our log resolution, and it's an isomorphism away from our singular point, and that the exceptional locus is actually a divisor. So, it being a log resolution, part of the definition of that is that this divisor, E, is a simple normal crossing divisor. So we can in that case, we can define the dual complex of the pair y comma e. So, that's just defined as it was before. And Stepanov showed that the homotopy type of this complex doesn't depend on the choice of the resolution. So of course, and this is a great thing, because when you think about resolution of singularities, well, in dimension 2 there's a minimal resolution, but in higher dimensions there's not going to be any, or not always going to be any distinguished resolution. You might have, 2 resolutions and you can't, you can't pick a smallest one. But this is showing that there's some invariant coming from the dual complex that is actually an invariant of the singularity. So in this case, it's the homotopy type. Now, unfortunately, we can't get that the homeomorphism type of the dual complex is independent of the choice of resolution, because you can think about, if you just take, let's say your dual complex was just a single point, and you just have one component just came from extracting a single divisor. But you can just keep blowing up and extracting more divisors, and let's say you're on a surface, then you can keep extracting more divisors by blowing up points on that divisor that you started with, and instead of getting a single point, you're going to get some graph. Now, the only thing this guarantees, though, is that this graph doesn't have any loops. So you're always going to get a tree. So now, of course, there are some singularities where, maybe you can't blow it up just once to get a resolution, and this dual complex can be more complicated. So nonetheless, so for a class of singularities called log terminal singularities, so these are singularities that come from the minimal model program. Dufresne, Kolar, and Xu showed that the dual complex of y and e is actually contractible. So, and the way they do this is they basically say, okay, well, in the case when you have a log terminal singularity, then these are kind of the good singularities with respect to the minimal model program. So this is a nice class of singularities because, in particular, when you have a log terminal singularity, it guarantees that your singularity is rational. And it also includes many natural singularities that are going to show up anyway that you would like to work with, including finite quotient singularities. So if you take a smooth variety and you quotient it by a finite group, then you're guaranteed to get a log terminal singularity. So this is already kind of a nice class of singularities. And it turns out it's one of the right classes to work with when we think about the minimal model program. So the idea was, so I talked about when maybe you're blowing up this surface and then you keep blowing up and adding things to your picture. So their technique was to just reverse that process, to say, okay, well, I start with my resolved singularity and I want to blow it back down by running these steps of the MMP. And what they worked out was that in this case, when you do the divisorial contractions or when you do the flips, that whatever you did, it was always some kind of, basic manipulation of your dual complex that gives you a homotopy equivalence. Let's see. Okay, so for one example, you can think about for surfaces, so kind of the simplest singularities on surfaces are the Duval singularities. So these come from particular quotients by finite groups. So it's, in particular, if you look at a subgroup of the special linear group, that's so if you take a finite subgroup with SL2C and you quotient C2 by it, you get one of these Duval singularities. And the classification of these singularities is by their dual graph, because if you work it out, the minimum resolution is always going to be some tree of P1s, and every P1 that you extract is going to be a -2 curve. So for the Duval singularities, it turns out that that these singularities are exactly in correspondence with the Dynkin diagrams of A, D, and E type. So the A-type singularities are actually toric, and then you can also think about the D and the E-type. And so here I've written down the equation for you. So if you take the vanishing of the polynomial x squared plus y cubed plus z to the 5th in A3, then that gives you an isolated singularity, and it has type E8. So in particular, that means if you take the minimal resolution of that, then the dual complex of the exceptional fiber, that exceptional fiber is going to be, some P1s linked together. They'll be linked together. That intersection complex is going to be a graph, and it's exactly the graph E8. Okay, so one thing I should add to this that's not on the slide is one of their applications. So one of the ways in which Defernet-Kohler and Shu used this fact was to study degenerations of rationally connected varieties. So the idea is that this is kind of my other motivation for thinking about dual complexes, is that you can think about them also when thinking about degenerations of varieties. So in that case, the idea is that you have some smooth variety, and you have a family of it, and then sometimes this family of smooth varieties, you can't complete it to a smooth family. You end up completing it to some family that's singular, where the special fiber has some singularities, but maybe you still want to just guarantee that it has simple normal crossings. And so you can do this by you take any way of filling in your family, and you just keep blowing up until you do some log resolution of singularities. So then you can say, well, let's think about the dual complex. And again, you have a similar situation where you can link different models of this degeneration via the minimal model program, and again you'll see, that this is another thing that they proved, is that the homotopy type of the dual complex of the special fiber is doesn't depend on the choice of way of filling in the family. And in fact, for the case where your general fiber is a smooth rationally connected variety, then running the minimal model program eventually gets you down to the case where you have some fibration over a smaller space. And that fibration is supposed to have Picard number 1. It's supposed to have relative Picard number 1. So if you imagine that the space you're fibering over was just the curve that's the base of your family, then having relative Picard number 1 means that there's only one component in the special fiber, because, well, if you have another one, then it was supposed to be contracted at some point. So this is saying that somehow if your minimal model program just gets you into this Mori fiber space situation over a curve, then the dual complex in that case is just a point, namely it was contractible. And so using these techniques, they're able to assemble an inductive argument that says for any degeneration of rationally connected varieties, no matter how you fill in the special fiber of that degeneration, you always get a contractible complex. Okay, so one final thing that they proved that will also be useful for us is that, so I've talked about how so the dual complex isn't an invariant in the sense that only its homotopy type is, but sometimes it's homeomorphism or PL type to be the invariant. So in this case, if you restrict instead of just looking at resolutions, but you look at what are called DLT minimal models. So I won't completely define what this is, but I'll just say in the case of a toric variety, the DLT minimal models of a toric variety, so the minimal models are always of a pair. So the idea is it's a minimal model of a variety with a divisor, and then you want the log canonical divisor, that's kx plus your delta, to be nef. And you want some condition on the singularities that you're not contracting too much stuff. So you don't, you want your delta to only have coefficients, bounded, you want the coefficients to just be 1, and you don't want, any cusps to show up, you don't want any bunching up, you only want these kind of normal crossings in the boundary. Some Duval singularities are okay, but not much worse than that. So if you think about toric varieties, well, for a toric variety, all the other toric varieties of the same dimension are other DLT minimal models, because you think every toric variety, it's a log Calabi-Yau, and you always have that kx plus delta is trivial, and the divisors that are exceptional, if you have a morphism, like a toric morphism between toric varieties, these exceptional divisors are all already in the boundary. So they're already showing up in this log canonical divisor, and so the fact here is that if you have any two toric varieties of the same dimension, well, the dual complexes of the boundary divisor are homeomorphic. In both cases, they're always going to be a sphere of dimension 1 less. So Dufresne and Koehler prove that there's a generalization of this for any kind of DLT minimal model. Okay, so I alluded to degenerations before, and this is the other place we're going to look for dual complexes. So of course, degenerations don't always have smooth limits, and this is especially true in the moduli of curves. So I have this degeneration of curves of genus G at least 2, so this is this is what you need to define MG, because otherwise you have too many automorphisms. So we have this stable reduction theorem that says, well, after a base change, you always get a stable limit. So you have to allow some singularities in your limits, but once you allow those singularities, then you can always write down a limit. So the fancy way of saying this is to say that MG bar is proper. So you do have to do the base change. This is kind of what the evaluative criterion of properness for stacks, because this has some orbifold structure to it, but the key here is that you can actually complete the family, and you can actually complete it in a unique way, if you just focus on stable curves. So if you allowed more complicated singularities, so the stable curves are the ones that have the nodes as singularities, and in particular, well, that's like a normal crossing almost, or at least analytic locally it's a normal crossing, so we can still define the dual graphs. So the thing I want to point out here is that if you have a stable curve arising as a limit of genus G curves, then the dual graph of that stable curve, or I guess you could also think of this, I'm abusing notation a little bit, but this is going to be the dual complex of the pair, which is the total family with the special divisor in it. Well, that dual complex is going to be a graph. You can define the genus of that graph, and the genus of your curve gives you an upper bound on the genus of the graph. So you can say even more. You can actually, because you can think of this stable curve as having an arithmetic genus, which you can compute from both the dual graph along with what the components look like. So of course, if you have two components of G1 and G2 joined like this, then the arithmetic genus of the whole thing is just G1 plus G2. But on the other hand, if you have a loop of curves of some genus, you have G1, G2, G3, etc., then in this loop you pick up, you increase the genus by 1 because you have the loop. So you get a contribution both from the genuses of the genus of each component and the genus of the dual graph. So this is a phenomenon that you can interpret it in many ways, but one way you can see it is that this is reflected in the Hodge theory of the degeneration, and in fact the homology of your dual complex is reflecting the, what's showing up in the weight zero part of the weight filtration in Hodge theory. So one thing I should point out here is that I'm being a little bit dishonest when I say stable curves have only nodes and singularities, so we may define their dual graphs. So I'm kind of insinuating, oh, I'm defining this the same way as the dual complex. But for the dual complex, I actually insisted that my divisors intersect transversely, that they were strict normal crossing divisors, and that in particular rules out having any self-intersection. So when I defined the dual complex to start with, I wasn't allowing any divisors that loop back around and hit themselves. But what you get when you think about mg bar is that you really do get curves that do this, that you're gonna, you just have to allow things that intersect themselves. And for curves, it's kind of clear what to do, because you just say, well, this intersection, I know what it looks like. It looks like a node. I can just think about it either in the analytic or étale topology. And in that setting, well, it just looks like a normal crossing intersection. So that means, I just stick an edge in there that connects the corresponding components. So that means if I have a curve that has a node, that it's a single component attaching to itself, the thing that shows up in the dual complex is that I have a point corresponding to that curve, and then the edge corresponding to that node just simply attaches to itself. And, again, you can still think about the genus of that graph. So everything's fine, but this is going to be a bit of an obstacle when we go into higher dimensions. Yeah, so the last thing I want to point out is that, so every stable curve arises as a limit of smooth curves, which is actually kind of a remarkable thing, that if, you can always smooth out these nodes. Okay. So the next thing we want to think about, of course, is surfaces. So for surfaces, as Professor Griffiths related in his talk, we also have moduli spaces. So these are going to be moduli spaces of surfaces of general type. So in particular, we want them to be canonically polarized, so that, if you start with a surface of general type, it might have some, -1 curves on it. It might have, so it has a big canonical divisor, which means that the canonical divisor and its multiples have a lot of sections, so that if you take proj of the canonical ring, that gives you something in the same dimension. And in fact, we know because of the minimal model program that it in fact gives you the canonical model. So this is a surface that's birational to the surface you started with, that may have picked up some singularities, but the advantage is that it has an ample canonical bundle. So in this setting, we also have moduli spaces in a stable reduction theorem, and this is due to Kohar, Shepard-Barron, and Alexeyev. So as Professor Griffiths alluded to, they're not using these kind of GIT techniques that were used to originally define the moduli space of curves, but instead you really have to lean on the birational geometry. So the idea being, you take some kind of large family, and then you run the minimal model program in the entire family to force it to be so that the fibers all have ample canonical bundle, because the minimal model program is something we can do in families. So this has a lot of advantages, namely that we can make it work. It has some disadvantages in that you don't really know anything about what the final product looks like, and it can be kind of a mess. So let's see where. Yeah, so in particular, this is like with curves. We still have to allow singular objects, and they still have to have non-normal singularities. So of course, just running the minimal model program forces us to have some singularities, but then these are kind of even worse. So it's not so surprising that you have to get these non-normal singularities, because, well, you shouldn't expect things to be better for surfaces than they are for curves. And for curves, you're already forced to pick up these nodes. So you should expect to pick up things like nodes for surfaces, but then you think about, okay, well, I have this nodal surface, and then I think about what's happening along that curve. So there's this curve where the surface is doubled, where it has nodal singularities, and then that curve might have multiple components, and it might itself have singularities. So the challenge is to kind of describe what's going on with this surface, how it's related to its normalization, not just along that curve, but also along the most singular points of that curve. Let's see. So one other thing I'd like to add about these degenerations of surfaces and these moduli spaces of surfaces is that it's not very promising to try and define these via GIT. Because even for surfaces, there's this thing that fails called asymptotic Chow stability. So this is, there's examples due to Wang and Xu that basically show that, for curves, the nice thing was that you could kind of get some control over what was actually showing up in your moduli space via GIT. In that, you'd think about these higher and higher canonical embeddings, and they would eventually stabilize to produce, one moduli space, and that was the moduli space of stable objects. And this is just no longer true even for hypersurfaces once you're in dimension 2 or higher. So somehow things get a lot more challenging when you think about surfaces, and it seems like there's a lot more going on. So we're allowing these singular objects, and they have non-normal singularities. So, and we can actually describe these in terms of the singularities of the minimal model program, but we don't know which ones are smoothable. And in fact, I think we do know that there are definitely going to be components of this moduli space that consist of only these non-normal objects. And, if we're interested in kind of the classical theory, which, is the motivation for all of this, we would really like to maybe just put these to the side and, at least for now, rule them out. We'd like to think about what's really showing up as a limit of smooth surfaces. So my goal for this is to, that's a little bit ambitious, so I just want to think about what's happening in the special fibers in terms of the dual complex. So again, you have this challenge in that, it's not quite simple normal crossings, in that, you have all this self-intersection. You have surfaces that are glued to themselves, and then that self-gluing along a curve is going to produce lots of self-gluing along points. And so, on a curve, it's kind of clear what to do. You say, well, okay, the components should be the surface components, and then the double curve should tell you how to draw lines between them. But then for filling in, it's maybe not so clear what you're supposed to do. Okay, so what are the singularities that show up? Well, you have what are called log canonical pairs, which are what appear in the minimal model program. So these are these generalized SNC pairs. So any SNC pair is log canonical. So I guess I should at least briefly tell you what the definition is. And that's to say that, I'll say kind of in words, is that the singularities you like in the minimal model program are the ones that allow you to take a top differential form, to take some canonical divisor and actually extend it to the resolution. So the idea is that locally, if you have some canonical divisor on your singular variety, so this is, you think of it as a wedge of differential forms, and then you can try pulling that back. Well, you can just pull it back as a line bundle, and then that'll pull back to something, on your resolution. But on your resolution, you have all these new divisors, and there's lots of ways to extend. Well, you can just use the pullback, which extends as a, just using the data from downstairs, just thinking of it as a line bundle, but you'd really like to extend it as a wedge of differential forms again. And so this necessitates that you pick up some zeros and poles along those divisors. And if you're picking up poles that are too bad, then this means you're going to fail to extend. So the log in log canonical comes in by saying, okay, instead of thinking about differentials, I'm thinking about log differentials. So I'm thinking about these wedges of differentials, these canonical forms, which have, which are log forms, in that they have poles along whatever my divisor is. So this means that I'm allowed to extend as a log form as long as I have no worse than a pole of order 1 at everything in my exceptional set. And so this is nice because this is exactly what happens when you think about blowing up an SNC pair. So if you imagine if you have two lines in A2, well, if you just take, you have dx over x wedge dy over y, and this is kind of the nice, in terms of toric geometry, the nice canonical form, because it's the unique canonical form up to scaling that has poles of order 1 at all of the torus invariant divisors. And this is somehow independent of which toric variety you pick. So if you do some kind of monomial blowup, no matter what that blowup is, this canonical form still has a pole along there. Or rather, you can extend that canonical form that was on the open set to one with over the toric variety as long as you allow a pole at each torus invariant divisor. So to incorporate SNC pairs in our theory, we have to allow this kind of behavior for the log canonical forms. And log canonical pairs are just saying, well, we allow any pairs like this. Now, when I say any pairs, I'm initially saying, let's force X to be normal. So you need X to be normal, you need it to have some kind of Gorenstein condition, so you can talk about pulling back these canonical forms. But it's really about pairs. So when we think about these stable families where we have something that's happening in moduli of surfaces, we have a smooth general fiber and a special fiber, and then we want to think about this in terms of the pair. So our special fiber is this weird non-normal thing, but we know what will happen is that we're going to get a pair where the total family with the special fiber is a log canonical pair. So we're also going to want to think about, well, what are the singularities of this special fiber? And in this case, when you have a log canonical pair, you say that the special fiber has semi-log canonical singularities. So the semi here is emphasizing the fact that you might have something that's not normal. So this is just the generalization of this theory to non-normal varieties. And the reason we need it is because of exactly this business with stable reduction where sometimes you get something non-normal in the family. But no matter what, you always get something semi-log canonical. So there's a nice description of semi-log canonical varieties in terms of their normalization, but I'm just going to focus on a special case. So the idea is going to be we start with let's just say an SNC pair, but it could also work for a disjoint union of them. And the idea is that D, let's say, is a bunch of surfaces. So we'll think about the surface case. And then B is going to tell you how to glue. So B is going to be what's all the double loci when you put everything together to get a non-normal variety. So if it were like a curve, B would be like the pairs of points you're identifying, and likewise for surfaces. So of course, B itself, I guess this definition is only for surfaces right now. So let's say that B itself is some curve, and that curve has some double points. So eventually we're going to think about the example of 4 lines in P2. But you can imagine, even that you have like the boundary of a toric variety or something like that. So you have a bunch of curves, and they intersect in these double points, and then I'm going to put some gluing data, which tells me how to attach this curve to that one. And part of that gluing data, one of the requirements I have on it is that the double points have to get sent to other double points. So away from the double points, you just have this 2-to-1 map, and then the double points, they might get piled up on. So you might get like a whole bunch of these double points. There's no limit to how many can be bunched up. But you have this pretty straightforward combinatorial description that tells you how to take this disconnected SNC surface and then glue those pieces together to get something that's not normal. So you take that scheme theoretic quotient, and that scheme theoretic quotient is always semi-log canonical. So my goal for today is to tell you how to produce a dual complex for these kind of semi-log canonical varieties. Okay, so I can define whatever I want, so I'm going to define my candidate dual complex, and then if I'm going to prove a theorem about it, I have to relate it to something else. So let's start with X delta, a threefold log canonical pair that has some, it satisfies some kind of, niceness conditions, so, some technical conditions that delta supports the Cartier divisor, and in particular, this is going to imply that X is Q Gorenstein. Well, okay, so this is in particular true of X is Q Gorenstein, and let's assume that if you take the normalization D of the divisor delta with the double locus B, that you get an SNC pair. And so then, to get back down to delta, you have this gluing data. So I'm going to use this gluing data to prove this complex. So the idea is you have B, and it has a dual graph. So what you're going to do is you're going to take that dual graph, and then you're going to take the barycentric subdivision. And so what that corresponds to is you think about each of your divisors D, and the dual graph, so taking this barycentric subdivision of the dual graph of a divisor is like doing blow-ups at each of the intersection points. So, formally what we're going to do is we're going to blow up each of those intersection points, do the gluing, and then contract them back down. So the idea is that the other reason to do this barycentric subdivision is because it makes the equivalence, the involution sigma, a little more well-behaved. So, you just think, okay, well, now the vertices of my graph are both components of B and intersection points, and then, if a component contains an intersection point, then there's an edge connecting them. And so now the sigma tells you, okay, well, this edge goes to just wherever, if B gets sent to this other guy, well, I send that vertex there, and then, wherever the image of this intersection point was over there, that's how I map the edges as well. So at the end, I'll show an example which will hopefully make this a little more clear. And so the next thing you do is you just take the cone over all these graphs, and then you use this equivalence relation to just take the topological quotient. And this gives you some topological space. So the theorem is that this is the dual complex in the following sense. So from before we had, so we were like, well, we don't know how to define the dual complex for these singular pairs. But thanks to the work of DeFernicola and Shu, we know that if I take a DLT minimal model of a pair, that no matter which one I pick, I always get the same dual complex up to homeomorphism. So it's actually up to PL homeomorphism, but I didn't want to, so this is work in progress, I should have said. And I think I do get homeomorphism and not just, I do get PL homeomorphism and not just homeomorphism, but I didn't want to state it on the slide. So the idea is that, you can say for a log canonical pair, we just define the dual complex to be the dual complex of this minimal DLT model, and it doesn't matter which one you pick because the answers you get are all homeomorphic. In fact, it's even better. You can just identify them via, you can think of these dual complexes always as spaces of valuations, and if you take two DLT minimal models, you're actually getting the same valuations. So the theorem says that this kind of direct description, just based on how you normalize the singular fiber, by taking that normalization, building a complex out of those pieces, and then doing some gluings according to the involution, gets you something homeomorphic to what's supposed to be the correct answer. Okay, so I'm going to talk a little bit about how one proves this, but I won't spend too much time on that. But the idea is that you have what are called log canonical centers of your pair, and these are kind of like the most singular parts. So these are going to be, for a DLT pair, these just correspond to pieces of your dual complex. And for a log canonical pair, you're going to have one for every component, one for every piece of the double locus, and then one for all of these really singular points where the double locus itself has singularities. So you can think of the pieces of the DLT minimal model as dominating these log canonical centers. And the idea is we're just going to divide up the dual complex according to what kind of center we're dominating. So dimensions 1 and 2, so the two-dimensional log canonical centers are just the components of delta. And so we know what dominates that. It's just the strict transform, and each one of those is going to give us a point. And then the idea there is that, well, how are these connected up? Well, they're going to be connected up according to what gets glued where. So, downstairs I'm going to have a one-dimensional log canonical center over each of these double curves. And so those double curves are telling me, oh, well, I'm supposed to have some segment attaching either, if it's a double curve on a single component, it attaches the component to itself, just like in the curve case, or it attaches these two components together, just like in the curve case. So the thing that's kind of tricky is understanding what to do with the singular points of the double locus. You have these double curves, and maybe itself it has a node. So you have to say, well, what's my contribution to the dual complex there? And to understand that, there's two things we need to include. So the first thing is to realize that in the DLT minimal model, the divisors that get contracted all the way down to these points, they really look like log Calabi-Yau varieties because the log canonical divisor is going to be trivial on them, and they get contracted all the way down to a point. And so our local picture of the dual complex, if I take a point corresponding to one of those divisors in the dual complex, the local neighborhood, so the star around that point, it looks like the cone over the dual complex of the boundary of a log Calabi-Yau surface. And we know what log Calabi-Yau surfaces look like. Well, they kind of look like toric surfaces, except maybe you blow up some points here and there. And in particular, the dual complex is going to be an S1. So that tells us that, locally we look like the cone over an S1, or that is a disk. So this says that, the dual complex, the total thing might not be a manifold, but at least the parts that are sitting over these dimension 0 LC centers is a manifold. And then the second part is just to use the previous work of Dufresne, Kolar, and Shu to show that, this part of the dual complex is actually contractible, and so, once you have a manifold in dimension 2 that's contractible, well, you basically know it's a disk. I mean, we also have to kind of keep track of what's going on kind of near the point, but you can actually identify in these centers in dimensions 1 and 2, kind of near one of these centers of dimension 0, a loop in the dual complex that you attach that disk to. Okay, so I think this is, this gives you some idea of the proof, but to really kind of understand it, we need some kind of example. So I'm going to think about these surfaces, so these surfaces that appear in work of Franciosi, Pardini, and Rolenska, just as Philip mentioned in his talk. So I'm taking kind of a different perspective. So these are going to be non-normal surfaces that show up as the limits of these I surfaces. So what we're going to do is we're going to build the special fiber as we did on the previous slide. So the idea is you take your special fiber, its normalization is going to be P2, and the double locus, the pre-image of that is going to be 4 lines. So you have to attach those 4 lines to each other. So we're going to say, well, let's say line 1 goes to line 3 and line 2 goes to line 4. But that's not enough information. So for one thing, we require that the 3 intersection points on line 1 have to go to the 3 intersection points on line 3. And likewise, for the 3 points on line 2, they have to go to the 3 points on line 4. And of course, the automorphism group of P2 just being dependent on where you send 3 points, once you make those assignments, then that's enough to completely choose your involution, but you still have to make those choices. So you might think that, okay, well, the intersection point of 1 and 3, if I'm sending 1 to 3, that has to go to that same intersection point. So that's actually not true, but it will end up being the case for this involution. That's just because, to get something in this degeneration, we have to pick a special one. But in fact, you could send the point on a wild ride and get a whole bunch of points being identified in the non-normal surface. And that's kind of why studying these things is a bit tricky, because you can get kind of these, very singular things in dimension 0. Okay, so, for certain assignments, these SLC surfaces actually appear as limits of smooth surfaces of general type. And they're specifically, the specific smooth surfaces I'm going to talk about are these I surfaces. So these are surfaces that have the following invariants. You have that the geometric genus is 2. The irregularity is 0, so that's saying that the surface is simply connected, and that the canonical squared is 1. So these are, as Philip alluded to, kind of the simplest surfaces of general type you can think about in terms of having small invariants. I guess there are some with PG equal to 1, but it turns out these have a particularly simple description. So the idea is, I want it to be of general type, and I want it to be canonically polarized in particular, so KS is actually ample. And so what I want to think about is, once you have a surface like this, you can use the typical kind of classical techniques to figure out how to embed it in some projective space so that we, know what it actually looks like. So, and this is, a kind of a fun calculation. So, the idea is, okay, the first thing we know is that PG equals 2, so we have this canonical series that has, 2 independent sections, so that gives you a pencil. So if you think about this pencil, then, you have to rule out, let's just assume that the pencil doesn't have a base component. Well, if it doesn't have a base component, then it has to have a single base point because k squared is equal to 1. So, the two members of the pencil have to intersect in a single point. And, if you think about what a junction tells you, Ks plus C restricted to C is, Kc, then the members of that pencil, the fibers, are going to be curves of genus 2. So, you can imagine this thing fibered over P1 after you blow up that point, or you can just leave the point alone and just have a bunch of these genus 2 curves, which are, of course, automatically hyperelliptic, going through that point. So let's say C is such a curve. And so now let's think about, the bicanonical series. So since we have that Q is equal to 0, then that tells us the irregularity, which is going to be H1 of O of the surface, that's equal to 0. So H1 of the canonical bundle is also going to be 0. So I guess I should have put H zeros here. So of course this is an exact sequence, but it's also exact when you take global sections. So if you take global sections, then you have 2 global sections on the left. Over here, it's a genus 2, so you have 2 on the right, and so you have to have 4 in the middle. And so you say, okay, well every section has to lift. So if you think about what you have your fibration, and if you square the fibration, that's over a P1, so you have the pullback of O of 2 on the P1, so that gives you 3 sections. That's another typo, isn't it? Okay. That gives you 3 sections which are like S squared, ST, and T squared. And then you have another section that comes from, that just lifts from the curve to complete the canonical series, so that gives you 4 sections. And then that induces a map so that, those sections you can think of as being generated by 2 in degree 1 and then 1 in degree 2. So that induces a map from your surface to a weighted projective space P112. So there's an extra 1 there, that's a typo, I apologize. But this P112 you can think of as being a singular quadric cone in P3. Okay, so more in fact is true. Is that we're going to get that this map, we want to think, well, what is it doing? Is it surjective? Is it, it can't be like an immersion because, well, this is a surface of general type and then this guy is rational. And in fact, you think about what this is doing, well, it has to separate all of the curves except for maybe the base point because, you have these degree 1 guys. And the canonical, it has to also do what the canonical series does to the curves. And it's a hyperelliptic curve of genus 2, so that canonical series induces the hyperelliptic double cover of P1. So what we're going to get is that this map from S to T restricts to the double cover from C to P1. So that means it's actually a double, and the image is each of the lines in that cone of each of those curves. So we're actually going to recover S as a double cover of T, and we just have to figure out what the branch locus is. So this branch locus is going to be some divisor on this singular quadric cone, and it's got to restrict to the branch divisor on each line. Well, there's a little bit that's not true there because, part of the branch divisor, if you think about that base point, when you double the base point, that's also one of the branch points because it's part of the hyperelliptic series. So, and then that one's not part of this divisor. So you actually get the cone point, And then on each line, you get 5 other points that are moving in a family. So that means the branch divisor comes from a quintic. So the branch divisor is the restriction of this quintic hypersurface to from P3 to this quadrant cone. And, and so on each line, it's giving you 5 points to branch over along with the cone point. And when you take this double cover, it's actually dealing with the cone point because that's a, that's an A1 singularity, and it's, just an orbifold point coming from Z2. So we can actually conclude, putting all this together, that our surface S is a hypersurface of degree 10 in this weighted projective space P1125. So, saying you have something in a weighted projective space that looks like this is really just the same as, oh, it's a double cover of this P112, and then this 5 is telling you what the branch locus looks like. Okay, so that's another way to, in kind of the classical way to understand these I-surfaces. And we want to produce a non-normal surface which is in this family, and we're going to do it in a way that comes from this construction from before by taking a divisor on P2, these 4 lines, and identifying them. So we're going to want PG equal 2 and K squared equal 1. And, well, to get this K squared equals 1, it's very convenient to take D being P2, B being these 4 lines, and then, the canonical divisor is really, of the non-normal surface, is really, looks like the log canonical divisor of the normalization with the double locus. So, if we take KD plus B, that's O of 1, and its square is 1. So we also need PG to be 2. So to make PG equal to 2, we just want, some pencil of lines to work with this identification. So the idea is that you have this pencil of lines, and I want the intersection point with L1 to get identified with the intersection point with L3. And likewise, I want the intersection point with L2 to be identified with the one from L4. And, you might stare at this and say, well, how do we know we can do that? Well, you can just sort of force it to be true by doing the following. So the idea is, you have the intersection, you have all your 6 points of intersection. And the idea is that, well, when I hit the intersection of 1 and 2, I should also hit the intersection of 3 and 4. Because if I'm sending the point on 1 to the one on 3, and that's the same as the one on 2, it should also go to the one on 4. So that line that connects those two has to be in our pencil. And so does the other line where I'm connecting P of 2, 3 and P of 1, 4. And then it turns out, well, once you make those identifications, and then you say, okay, well now, P1, 2, I have nowhere to send it. Well, it's just supposed to go to itself. And, P of 1, 3 is supposed to go to itself. P of 2, 4 is supposed to go to itself. And then that data is enough to specify this entire identification. It tells you, that's enough to tell you sigma. Okay, so as above. So, once we've made these choices, the identification of L1 with L3 has to send 1 to 3, 2 to 4, and 4 to 2. And likewise, the identification of L2 with L4 has to send 1 to 3, 3 to 1, and 4 to 2. And then you can work out, that, once you've done that, this pencil of lines really does have this property. Okay, so these identifications are going to produce an SLC surface. And in fact, Françoisi, Pardini, and Relensk show that this SLC surface has Q equals 0, so it's supposed to be in this family. And it also embeds as a degree 10 hypersurface in this weighted projective space. So that immediately tells you it's a limit of smooth guys because you can just, kind of nudge it in some direction. And, you get one of these smooth guys. And so, the converse is also true that these, these I-surfaces, if you just take a general hypersurface in here, then you can just, this has, singular point, but you just avoid the singular point, and then you've got a smooth hypersurface, and you just check what the invariants are. Well, you have PG equals 2, K squared equals 1, Q equals 0. Okay, so what does the dual complex look like? So this is my penultimate slide, but there's nothing on the last one, so I'm going to close soon. So, okay, so this is like, this is a big diagram that it's like, it's unclear what it means, but the idea here is that, you got to remember what the theorem said. So the theorem said is that the way that you produce this, this dual complex is you start with the graph of the double locus divisor. So if you think of P2 and the 4 lines, then from the beginning that gives you the graph K4. So here we have the graph K4 right here. So you have 1, 2, 3, and 4. And I have blown up some points, so I've done the barycentric subdivision, although I didn't do it the whole way around, because it turns out for these identifications you don't have to do it all the way. But I've made identifications of the edges coming off from 4 with those coming off from 2. You can see there's the D here is going to be identified with the D here. The A here gets identified with the A here. And the B here gets identified with the B here. So likewise, I get the same identifications between kind of the local neighborhood at 1 with that at 3. So this is exactly what my gluing is telling me to do to the cone over this graph. So the idea is I take the cone over this graph, and then I make these gluings. And so it's kind of hard to visualize what that looks like. So instead, I drew it down here in this picture right here. So what's the relationship between these two pictures? Well, let's think about taking the cone first. So the idea is when you take the cone over this K4, it looks kind of nasty. Because, you know, you're taking the cone over something that isn't a loop, so you're going to get something that's not a manifold. You're going to get, you know, singular points. You know, in particular, you know, you have these singular points right here because you have, you know, this trivalence, whereas you need bivalence to have something that's manifold. So instead what we're going to do is we're going to say, well, actually, you know, if I want to just recover this K4 from something that's a manifold, I can just think of gluing some loops together. So if I take the loop, you know, A, D, A, C, so if I go like this, so I go around A, I go around D, I go around A, and then I go around C, well, that's one loop in this graph. And then I can also go around the loop, you know, B, D, B, C. It's another loop in this graph. And gluing those two loops together on the obvious identification, just of, C to C, D to D, as we see here, that recovers the cone over this graph if I take the cone over these. So the cones over these are just disks. They're just closed disks. And so the idea is that, well, I need to figure out how they're identified. Well, the identification before I do the gluing is that this A here is identified with that A there. This B here is identified with this B here. And, you know, that's glues my things together. And so now I just have to, you know, attach according to the equivalence relation, and I've got whatever my dual complex is. So now I just do the operations in the opposite order. I say, well, let's just glue along the boundary first, and then do the attachment along A and B. Well, here you can see, well, I'm just folding over this C to this C, because I'm attaching 1 to 3. I'm folding over this D to this D, so I have, like a pita with an open top, and then I'm just gluing the A to the A. And so that makes a sphere. So this is topologically a sphere after identifying these edges like this. Likewise, this is the same picture, so it's also topologically a sphere. And then these spheres are just glued along A and B. And in fact, if you think about it, this is actually homotopy equivalent to the wedge of two spheres, because you can kind of just shrink down, you can kind of move around the A and the B and shrink them down to a point. So this, gives us something we didn't know before, was that the dual complex of the DLT minimal model of that degeneration is homotopy equivalent, is actually is this complex, which is homotopy equivalent to the wedge of two spheres. Okay, so I think this is a good stopping point. I just have one slide which is like higher dimensions, but I don't really have much to say about that. So, other than I don't know. Okay.
Any question? What do you do about the pinch points?
So like pinch points like in the Whitney umbrella, or the place. So those don't actually show up in the dual complex because they're not contributing any log canonical centers. Yeah.
And what do you do
Oh, the normal singularities, so those you can, so the assumptions tell me that I don't have any elliptic singularities.
Oh,
So if you have elliptic singularities, then you have to throw those in. So there's like, you know, there should be a more complicated theorem for when the normalization has elliptic singularities.
See, this doesn't see embedded points either.
You won't have embedded points. That's like the total thing is always going to be like S2 or something. So you don't have any embedded points in the special fiber.